What if you could somehow drill a hole straight through the entire Earth and then jump in? How long would it take to reach the other side, and what would happen along the way? Let's start with the basics. We're talking about a tunnel that goes straight through the planet, from one side to the other, passing directly through Earth's center. It's about 12,742 kilometers of free fall through rock, metal, and some very uncomfortable temperatures. Most people think this would be a quick trip, maybe a few minutes of falling and you'd pop out somewhere in China. The reality is much more interesting, and significantly more deadly. For decades, physicists have been fascinated by this exact scenario. The traditional answer was that such a journey would take about 42 minutes and 12 seconds. But recent calculations using real seismic data suggest it would actually be closer to 38 minutes. The difference comes down to how we account for Earth's varying density. The planet isn't uniform like a basketball. It has layers with different densities, and when physicist Alexander Klotz crunched the numbers using actual geological data, that 4-minute difference emerged. Think of it like this. You're essentially riding a water slide that takes 38 minutes to complete and accelerates you to speeds over 8 kilometers per second. That's nearly 18,000 miles per hour. You'd be moving faster than most spacecraft when you hit maximum velocity at Earth's center. But here's where it gets really fascinating. The motion follows what physicists call simple harmonic motion. You wouldn't just fall straight through and shoot out the other side into space. Instead, you'd oscillate back and forth like a pendulum, with Earth's center as your equilibrium point. You'd fall down, overshoot the center due to momentum, slow down as gravity pulls you back, then reverse direction and fall toward the center again. The gravitational dynamics change dramatically as you travel deeper. Once you're below the surface, the net gravity acting on you depends only on the mass between your position and Earth's center. As you go deeper, there's less mass below you pulling you down, so gravity actually decreases. At the exact center, gravity would be zero because there's equal mass in all directions exerting equal pull. Now, this assumes our planet isn't spinning, which brings up another complication. Earth's rotation introduces something called the Coriolis effect. An object dropped into such a hole wouldn't fall straight down. Instead, it would drift eastward and eventually hit the wall of the tunnel. This happens because as you fall toward the center, you're moving to areas where Earth's rotational speed is different. The Soviet Union actually tried something vaguely related to this thought experiment. From 1970 to 1989, they attempted to drill as deep as possible with the Kola Super Deep Borehole project. They managed to reach 12.3 kilometers before stopping, which is roughly 0.1% of the way through Earth. Even at that shallow depth, they encountered temperatures of 180 degrees Celsius instead of the expected 100 degrees. And the rock became so hot and plastic-like, the drill bits kept getting stuck. Which brings us to the uncomfortable truth about what would actually happen to you on this journey. After falling just over a kilometer, you'd encounter temperatures that cause heat stroke. By 2.7 kilometers deep, your bodily fluids would start boiling. At around 200 kilometers down, which is only 3% of the way to the center, you'd be completely incinerated, with only dust remaining to complete the journey through the remaining 200 kilometers. The temperature at Earth's core reaches about 5,400 degrees Celsius, nearly as hot as the sun's surface, with pressures over 3 million times greater than what we experience up here. But let's imagine for a moment that we could solve the heat problem with some kind of futuristic protection suit. Even then, your journey would be far from the quick drop most people envision. The air density would change dramatically as you fall deeper into the planet. What starts as normal atmospheric pressure at the surface would gradually thicken into something resembling soup by the time you're halfway down. This increased air density would act like a natural braking system. Instead of accelerating continuously until you hit maximum speed at the center, you'd actually reach a terminal velocity much earlier in your descent. With all that atmospheric resistance, your maximum speed would be limited to around 200 kilometers per hour, turning your 38-minute physics textbook journey into a week-long slog through increasingly dense air. The geological layers you'd pass through tell their own fascinating story. First, you'd drop through the relatively thin crust, which is only about 30 kilometers thick in most places. That's barely getting started. Next comes the mantle, a massive layer of hot, semi-solid rock stretching nearly 3,000 kilometers. The mantle isn't uniform either. Near the crust, temperatures hover around 700 degrees Celsius, but by the time you approach the core boundary, you're looking at 4,000 degrees. Then there's the outer core, a churning sea of liquid iron and nickel about 2,300 kilometers thick. This is where Earth's magnetic field gets generated, and the temperatures range from 4,000 to 5,000 degrees Celsius. Finally, you'd reach the inner core, a solid ball of iron and nickel under such intense pressure that it remains solid despite temperatures that rival the sun's surface. Interestingly, if we could somehow create multiple tunnels connecting different points on Earth's surface, the travel time would remain roughly the same regardless of where you start and end. A tunnel from New York to London would take about the same 38 to 42 minutes as our straight-through journey, even though it's a shorter distance. This happens because shorter tunnels also experience weaker gravitational pull, and these two factors cancel each other out almost perfectly. The engineering challenges of creating such a tunnel are beyond anything humanity has ever attempted. We'd need to maintain a perfect vacuum to prevent air resistance issues, construct walls capable of withstanding temperatures that melt most known materials, and somehow account for the immense geological forces trying to crush the tunnel shut. The deepest we've ever managed to drill is less than 0.2% of the way to Earth's center, and that project pushed our technology to its absolute limits. Even if we could build it, the tunnel wouldn't stay open for long. Tectonic activity, thermal expansion, and the sheer weight of the surrounding rock would constantly threaten to collapse our passage to the center of the Earth. So where does this leave us with Marcus's question? In the realm of pure physics, falling through a hole across the Earth would be a 38-minute journey of simple harmonic motion, reaching speeds that would make jet pilots jealous. You'd oscillate back and forth through the planet's center, like the world's most extreme pendulum ride. But in reality, this thought experiment quickly becomes a cautionary tale about the incredible forces lurking beneath our feet. Within the first few kilometers, you'd succumb to temperatures that turn rock into plastic and human bodies into vapor. The journey that seems so elegant in physics textbooks transforms into a brief encounter with some of the most hostile conditions in our solar system. The fact that we've barely scratched the surface with our deepest drilling attempts puts this whole scenario into perspective. The Kola project's 12 kilometers represents humanity's absolute limit so far, and that's roughly equivalent to poking a needle into a basketball. We're still incredibly far from understanding everything about what lies beneath us, let alone traveling through it. Perhaps the most fascinating part isn't the journey itself, but what it reveals about our planet. Earth isn't just the ground we walk on and the sky we see. It's a dynamic, layered world of extreme temperatures, crushing pressures, and geological forces that dwarf anything we experience on the surface. The next time you're standing outside, remember that just a few kilometers below your feet, the conditions are already lethal, and thousands of kilometers down, there's a core nearly as hot as the sun itself. Makes you appreciate that thin layer of breathable atmosphere and comfortable temperatures we call home.